So our final rule for assigning oxidation numbers has to do with polyatomic ions. And the rule is that the sum of the charges on all the atoms within the ion has to add up to the overall charge on the polyatomic ion. The example we're going to use is chromate, which has an overall charge of -2. Just like we did with the compounds earlier, we want to start with the element that has a rule. In this case, that's oxygen. Oxygen has a rule of -2. The exception to the rule would be when oxygen is in a peroxide or combined with fluorine, and neither of those are the case here. So I have it set up to do the math on the right. The subscript tells us we have 7 oxygens total. Each of them has a charge of -2, giving us a total charge of -14 on all the oxygen atoms combined. Now, we said the overall charge on the chromate ion is -2. That means the remaining atoms, which are all chromium, have to total +12 in order to add up to -2 to combine with -14 to get -2. Well, the subscript on chromium tells us we have 2 atoms, so now it becomes an algebra problem. 2 times what number gives us +12, and that number is +6, which means the oxidation number of chromium in the chromate ion is +6. As long as we look on the periodic table and find that +6 is a choice, and assuming we've done the math correctly, then we're all set. A major point I want to stress here when it comes to polyatomic ions is the fact that compounds that contain polyatomic ions have both ionic and covalent bonds. I'm going to go back a few pages to illustrate this. And I'm going to take a look at 2 examples. The first example is with a positive metal and a negative polyatomic ion. Now, the bond between the metal and the polyatomic ion itself that combines the 2 of them is a bond between ions, which means that's an ionic bond. But if you look at the atoms within the polyatomic ion, you have 1 nitrogen and 3 oxygens, all of which are nonmetals. And what we said before is that bonds between nonmetals are always covalent, which means anytime you have a compound that contains a polyatomic ion, you have both ionic and covalent bonding. We'll look at one more. In this case, we have a positive polyatomic ion bonded to a negative nonmetal ion. Again, the bond between the 2 of them is a bond between ions, which means it's an ionic bond. But if we look within the polyatomic ion, it's a nitrogen and 4 hydrogens, all of which are nonmetals, meaning these 4 bonds must be covalent. So anytime you see a question asking you to identify a compound containing both ionic and covalent bonds, you're looking for something that contains a polyatomic ion. The last thing we want to do is just practice using table E on in your CRTs. That's on the second page at the top. We just want to practice identifying the polyatomic ions because that's a sticking point for a lot of people. And so I'm going to teach you how to separate these. Using table E, you look to identify, you'll find a polyatomic ion here and a polyatomic ion here. The subscript tells us we have 3 NH4 ions, and we have 1, and that's a plus, NH4 plus, PO4 3 minus. It's important that you make sure to include the charge. The next one is tricky. There's actually two ways to break this up. I said I'd do the first one. I'll do the first two with you. There's two ways to break it up. First, you could break it up here. Say you've got sodium, which is not a polyatomic ion, and HCO3 minus, the bicarbonate ion. Or you could break it up another way and say that you have a CO3 2 minus ion. To be honest with you, that's the more correct choice because the NaH doesn't exist together. So it's the HCO3 that you'd be looking for. All right, so I'm going to go back and leave it broken up this way. So try the next three on your own, see how they work out, and then just complete this part here just to sort of finish the exercise and make sure you understand the concepts. Come in with any questions that you have tomorrow regarding any of this or specifically polyatomic ions.